All right, so in this video lecture, we are going to start looking into the polynomials. It's a one class of functions out there, okay? And it's a very important class of functions existing out there. So take every instruction from this video lesson as closely as possible, because what you're looking at now has an unlimited amount of details out there, and believe me, there are PhDs out there who spend their entire lifetime studying about these functions, the functions in this class of functions here, the polynomials. All right, and so before we begin our journey here, it is required that this lesson must be viewed after you have already learned about what a function is and all the graphical behaviors of the functions. Okay, and you have seen enough and you have been familiar enough with all of the important concepts of a function, as well as a domain and range and all of that. Okay, and also it is beneficial, even though not extremely required or not highly recommended, but it is very beneficial that you view this lesson after you have also learned about transformations. Okay, all right, but other than that, here we go. Let's start diving in. And for this particular lesson, now I will slightly change my approach in terms of giving the examples a little bit. So, as you have seen my earlier and many of my other video lectures, then examples where I number will be direct example that's directly connected to the material currently going on. But as I said earlier, this kind of material we're about to learn about polynomials, we only learn enough with the kind of details suitable for our level here, being a pre-calculus course, but there are a whole world of details out there regarding these polynomials. And so in that way, outside of those examples where I number, which brings up problems directly related to the learning material, I will also introduce along the lecture here, or I will blend in here and there with those examples where I call the apply examples, where we're gonna mix the details that we've learned together into one example. And now, so when it gets to those applied examples, I won't number those examples. I will clearly state that they will be, any of those brought up will be applied examples, and they won't get a number. Okay, and then with those examples, there will be no hard rule about how many of those examples I can guarantee that I will be able to deliver. Okay, because those are just examples where they really are problems where we apply all of these details in so many different angles, in so many different ways. All right, and anyone learning in this lesson will explore more as we get into that. All right, so now to begin with our journey here. Any polynomial, in my style of teaching about polynomial, we have to start out understanding the following. So it's a subclass of polynomials, and so let's get into it. Now, I don't want anyone to worry about what a polynomial is exactly right at the beginning. Let's look at the following. All right, so at least up to this point, as I've said earlier, you must have learned and have enough experience with functions. So when I was giving lectures about functions, I introduced what's so-called the toolkit functions for students who are in pre-calculus or college algebra. Okay, so among your toolkits function that I've mentioned in earlier lectures, then you have seen the following function. Let's say f of x equals x squared. All right, so no doubt about it. This function must have been seen in earlier lectures, and this function particularly must have been brought up a lot throughout many other lectures prior to this study about polynomials. Okay, so as far as the name, I call this particular function the simple quadratic, okay? But let's put names aside. Among your toolkit function that you have seen, we have also seen this one. All right, f of x equals x. So as far as the name to be one among those toolkit functions, I call this the identity function, okay? You have also seen f of x equals x cubed. All right, and so again, this was and currently is among the toolkit functions where I call this, well, as far as name, I call this, it's a simple cubic. Okay, but once again, let's put name aside right there. with these three, and I'm not saying these are all from the toolkits function that I want to bring in. I will even mention more. But for now, I brought in enough. Okay, so among these, well, yes, as far as name, this one was once again called the simple quadratic. This is the identity function, and this is the simple cubic. Okay, but this is one common thing that exists throughout all of these three functions right here. Any of this? So this one here, let me make a note of that too. So with this one here, the anatomy of that is that it's a variable x but being raised to power 2. Okay, so the variable, the input variable is here. Okay, and so the rule of this function specifically is whatever input variable that is, the rule says we're gonna raise that to this power 2. Okay, and this power here is given. So once the function is defined, the power stays the same. But again, the rule of the function says we can change to different inputs. We can change from inputs to inputs. But the rule says once we have that rule given, right, then this power stays the same. It's not going to change when we're giving a different input. Okay, so the inputs can be changed, but this power stays as the rule of the function. All right, and so now we already recognize that similarity with this function down here. Again, this part here, the x is the input variable. Okay, but this 3 right here is regarded as the power. Okay, and it's given. And so now to be specific, this is given power 2. This function here is given power 3. So they have that between these two, the simple quadratic and the simple cubic here, we already recognize that common anatomy. That's how I called it. It sounds like a biologist, but you see it has body parts. The input variable is, okay, and then we raise it to, this is square power or power 2, we raise this to power 3 right here. So it's the inputs being raised to a power. All right, so two functions had that, two of these functions already have that common the characteristic, okay, or common anatomy of that function. So what about this function here that I didn't get to that yet? We call that back in the toolkit functions. We call this the identity function and all that. And it's not written out so trivially, but here it is. We don't see a power like these. Algebraically, it means power 1. Okay, so now that nature, it has the same, this function all of a sudden we realize it has that exact same nature compared to the other two functions. So the input variable is here. Okay, so that's the input. Okay, and variable, allow me to use the shorthand writing. And then this is this part here is the given power 1. Okay, and again, so very same with the other two functions right here. Once the power here is given, it stays permanently as part of the rule for this function. So as long as you work with that function again, then we have to raise that to power 1. As long as you work with this x squared function, we have to always raise the inputs to power 2 because the power is the rule. It's part of the rule. Okay, and then as long as we're working with the cubic, the simple cubic here, then the power here is given. It's a fixed. It stays permanent in this power right here, in this function right here. Okay, inputs being raised to the third power. All right, so now after carefully investigating the three functions here that I put together, okay, then now we drew out a general conclusion. How about we drew out that general characteristic among these three functions here. So what they all have is a given power. In this function, it's a given power 2. In this function, there are three separate functions. In this function, is a given power 1. Input raised to the power. Input raised to the power. So now, generally speaking, on this board of mine right here, the function we recognize here is the inputs. The inputs, okay, but being raised to a power. How about P? All right, see, power 1 giving us the x to the first power, just f of x equals x. Okay, that is the identity function. f of x equals x squared. If p equals 2, f of x equals x squared. Okay, that's the simple quadratic. And then f of x equals x cubed from the other board. That's p equals 3 right there. Okay, so now, ladies and gentlemen, now I introduce for you this function right here. So now it's not just one function, it's a whole class of functions. And we can see that there are many different members already. There's a f of x equals x, the identity, which is the case where p equals 1. Okay, there was f of x equals x squared, as you have seen earlier from my other board. That was the case where it's the simple quadratic. So it's 2 members so far. And then we have seen the third one was f of x equals x cubed. Okay, that's when p equals the 3. Okay, so generally we refer to this, ladies and gentlemen. This is power. Any function in this form is called a power function. Okay, a function in that form, strictly in that form. The input variable, okay, being raised to a power. So now make a note of this. P is given, okay, as the power. I try to reduce the amount of wording, but I explain more in that. This power, once given in your function, it stays permanent anytime we're working with that function again. Okay, so generally speaking, f of x equals x raised to the power p is regarded as a power function. Okay, and what it has here is the inputs is the inputs is being the variable, is being the base. Okay, now that's just the common algebraic term. Allow me to assume a little bit earlier that you are already familiar with those terms. We call that the power, we call this the base, we call this the exponents, we call this the base. So the input is playing in the role of the base, but the power, once given, it stays permanent. Okay, so we can make note of that. Okay, x is the base, and x here I mean the input variable. All right, and so now I'm not saying that the base, I'm not saying that the power here always have to stay positive. Now, so far with these functions, I brought up to bring you into this family of polynomial, I brought up these familiar functions, and they all have given power being positive power being positive power. Okay, but now as far as just a formal definition, a formal generalization of power function, p, this power doesn't even have to be positive. Okay, that p doesn't have to be positive. It can just be any number, actually. It can be any number, and we will get to those. We will get to those. All right, but so now at this point, a power function really is a class of functions where it's anywhere we have, anytime we have a function in a form that the base being the input variable and raised to a given power. Okay, and the power p, there can be any number. All right, and so it's called a power function. All right, so now to trigger your attention even further, okay, I'm leaving this general form of a power function here. On this board of mine, allow me to erase those that or maybe I can just erase these extra notes right here that I've made. Okay, and I'm gonna introduce more members in that same class. So now we know these 3 functions, they're all in that same class. They're all in that same class of being a power function. This is the identity function, but really it's x to the first power. Okay, this is the one I erased. So this is x cubed, this is x squared. All right. And so now, sooner or later, when you arrive at the higher course, particularly the calculus 1 right after this course right here, okay, or maybe the two courses after this one, calculus 1, is where you're going to start seeing these kind of power function, these other members in the power functions. Now, you have seen f of x equals square root of x. No doubt about it. We have seen this back in our toolkit functions. This is one member among our toolkit functions. Okay, so this is indeed, now in our algebra understanding, a square root is regarded as a power 1/2. All right, a square root is regarded as a power 1/2. So in that way, now clearly this function is a member in our power function member. I mean in our power function class of functions. All right, so because f of x equals square root x is x raised to power 1/2. So once it's given, this power stays the same. Again, the input variable changes. Okay, so as long as we're working with square root of x function, again, that given power 1/2 stays the same, stays permanent in that function. Okay, only the input variable here gets changed. And again, the input variable, we can change a different value and it's acting as the base. The power stays fixed. All right. There's more. We have, how about among our toolkit functions? We have cube root of x. We have cube root of x. All right, we have cube root of x. So cube root of x now alongside with what I have explained earlier, in our algebra understanding, any root can be thought of as a fraction, similar to that earlier case right here. Square root is thought of as a power 1/2. So here cube root, we can think of that root as a fraction power. So this is the same as, this function is indeed algebraically the same as x raised to the 1/3 power. There I have just now displayed this function as a power function. I just represent this function now as a power function, and I brought to light that this function is indeed one member in the entire family of power functions. All right, this is not all there are. Okay, and we have seen 5 toolkit functions so far. They're all from our power functions. Now you can realize that the power function is so important. Okay, very important. One family of functions already cover 5 of our toolkit functions, our friendly toolkit functions so far, very commonly used out there. All right, what else do I see? So again, I stay very focused on the toolkit function for now to bring it to light that we have been working with these since long ago, but just now I made that realization for anyone viewing in this lesson as a continuation from our past experience. Okay, so now among our toolkit functions, we have worked with quite a few times throughout many other lectures right here. We have worked with 1/x. All right, now I'm not particularly worrying about domain. So power function is just the kind of function where I introduce that form. Anytime it's in the form of an input being raised to a power, we call that it's a power function, and it's a member, or at least it's a member of the power function class. Okay, but I never regard anything about the domain or anything like that, so don't even have to worry about that yet. But so how is this a power function? How is this one I just brought up here a power function? This is one thing we know algebraically. This is the reciprocal of x. Okay, 1/x. Formally speaking, what we call it's that name. It's the basic reciprocal, or it's simply just the reciprocal function. But reciprocal algebraically means this is x to the -1 power. So this is that given power, and once it was given, it stays permanently with our function as long as we're still working with that function. Only the input variable changes. Okay, and so the input variable again is the base. The power here is given, and it stays permanent, and it's a number. All right, 6 functions among our toolkit functions are power functions already. Okay, so, and there's still more. So what about, we have seen this reciprocal squared, or squared reciprocal, 1/x squared. All right, in our understanding in our algebraic understanding, this is the reciprocal of x squared, but anyone will know this. This is x to the -2 power. I just now re-expressed 1/x as x to the -1. I re-expressed 1/x squared as x to the -2 power. That's -2 power. Okay, so this is a power function. That is power function. All right, that is a power function. It's just a matter of we apply our algebraic understanding to and re-express these expressions, and now we display them, we redisplay them, we re-express them as power functions. Okay, so these are all power functions. This squared reciprocal right here is x to the negative 2. So that given power is here. The input variable is here. We can change the input, and the input is playing in the role of the base here. And the power is once given, it stays permanent throughout our function. So it doesn't matter what inputs we're giving it. We're always going to raise the inputs as part of the rule for this function. We raise the inputs to the negative 2 power. We must have learned something about domain and range. I am not focusing on any of that yet. We will bring those understanding in later. Right now, I just need viewers, learners from this lesson to understand what a power function is. All right, what a power function is. So, along that way, and there's still more. There are still more within our toolkit functions that we have learned. Okay, but now along that way, let me introduce you to example 1, quite direct example. It's just an example where I get you comfortable with recognizing, because sooner or later when you arrive at your formal calculus 1 course, okay, you will utilize this skill very intensively right there. So allow me, some instructor teaching pre-calculus do this, some instructors don't. I belong to the group of instructors who feel the need of giving this example right here as that vital skills that will carry on with you when you arrive at your calculus 1 course right there. Okay, so now I have left this here long enough. Allow me to erase this, and we're still focusing on the power function. So now you have seen earlier that I've listed all of those toolkit functions as, and there were ways to algebraically re-express those functions as power functions. So now I'm going to introduce example 1 right here. And like I said, this is my own example, directly relevant to the material we're doing. But some other professors who are teaching pre-calculus 1 cover, some other professors don't. I belong to the group of professors who cover this kind of example where I feel the skill you're about to do here is vital in your calculus 1 course and the later courses. Okay, so how about there are so many ways of wording it. You can say identify or re-express. There are so many ways of saying it. Okay, identify or re-express, or even recognize. Okay, there are so many ways of wording this, the following problem right here. So identify or re-express or recognize each of the following functions as a power function. Okay, we're not even trying to determine if it's a power function, yes or no, but any of the functions I'm about to give you is known to be a power function, but it's written in a form that's out of ordinary. Okay, so again, let me remind you what it means by being the ordinary form here. We just need to simply display inputs as the rule raised to the power p. Okay, as long as we reach to that goal, re-expressing our function into this form, inputs raised to a power p, we're good to go with that, and we say that our function there is clearly a power function. Okay, so we're going to have a whole bunch of functions given, and we know in the back of our mind that they are already power functions, but we just want to put them in the proper form, the ordinary form. That's what the intention of this example is. All right, so part A, good experience for anyone. You will see a lot. You have seen this a lot in your previous courses, and here I'm bringing these up again. How about f of x equals it's a 4th root of x. So this one here is similar to the square root function or cube root function that I brought up among the toolkits functions. So this is easily, and algebraically with our algebra understanding, then this can be easily re-expressed as x to the 1/4 power. All right, so that's simply it. see, the function itself maybe at first given was not so well recognized as a power function, but now with our algebra understanding, we can just re-express, or we identify this as a power function. So the given function here start out in this form, in root form. I re-express that as a power 1/4, so x to the power 1/4. All right, so now once you see where I'm going with this example, I can now start bringing in part B, and I'm still leaving, I have enough space because these are just little expectation in these and simple problems, so we still have a lot of spaces here. So I'm still leaving part A here. So how about f of x equals, how about, yes, it's cube root, but inside of the cube root, right here we have x to the 5th power. Well, in your previous courses, you've spent all of those times about simplifying roots and all of that. But the point now is, how do I see this? How do I see this as a power function? So I don't need anyone to simplify or reduce your root or whatsoever. This is a cube root, and inside of the cube root, we have an x to the 5th power. All right, so now with our understanding with our algebra understanding from past courses, I see this as x to the 5/3 form. So this is now I've just successfully re-expressed or identified or recognized my given function here as a power function, where the base here is the input variable. We can change values anywhere we want, any way we want. But that power, once we recognize it, once we have recognized it, it will stay permanently in this function. All right, and so now in that way, so just think about this. Now I'm not talking about the final form, but see this same function here. So allow me to draw that straight line right here to indicate this is the final ultimate power function form. Okay, but the same function here, see, if we applied the skill in reducing roots and all that, so this same function can also be thought of as, after reducing, it's x times cube root of x squared. So what I'm trying to say now is that this form sometimes is given instead of that. It's the same function, but sometimes we're giving in reduced root form. This is also the same as that exact function. Okay. All right, so there are quite a few different ways of seeing that now. Allow me to introduce the next problem. And we're still in example 1. And now I need to clear out the board space here. All right, so let's look at part C of our example. So you have seen those reciprocal thing, and that should be simple enough, so there's no need to beat around the bush. How about let's get straightforward into something like this. How about f of x equals 1 over square root of x cubed. 1 over square root of x cubed. So it has a 1 over something. Okay? So it looks like it's a reciprocal. It looks like it's a reciprocal. So there are quite a few ways of seeing this. Okay. You can see this as the reciprocal of that's just one way of arguing it. I'm saying that this is only one way of arguing it because I see a 1 over. So I take the whole thing in the denominator, see that as this whole expression now as the reciprocal, so power -1 already blending it. Okay, the reciprocal of square root of x cubed. And then with our understanding in algebra, okay, this square root of x cubed, and we can now start blending in our experience from part A and part B of this current example. It's just right before this particular problem only, not too long ago. Feel free to roll back on the video to see what we have done in terms of handling root and then having power inside of root. So now, completely inside of this -1 power, I see this square root of x cubed is recognized as x to the 3/2 power. And then the whole idea now is that we're taking the reciprocal because that's what it's a 1 over all that. And again, my route here is just only one way of arguing the problem. And for anyone who is already advanced in recognizing these, you don't even have to go that workaround. Okay, I'm just delivering the material for anyone entering the class here with the minimum amount of background in prerequisite courses. So these skills I brought in, you know it, but how you apply these skills, that's what I call, some people already got advanced, some people still at the minimal level. Right? That allowed me to introduce this way of arguing it for the people who have the minimal amount of experience. Okay. So now we have a power and raised to another power. So now this is x to the minus 3/2 power. This is how I've said I have finally identified or re-expressed or recognized my function here at start to be in a power form, to be a power function. This is x to the minus 3/2 power. Well, this is only one way of arguing it. Okay, I can alternatively show a quick other way right here. A quick other way. How about that? Quick other way allow me to write in a different ink color right here. And as I said, any of these, it's just, you know, as your prerequisites how to see these as powers. That's from your prerequisites. No one can argue about that. But how we apply those, now it can be different route to get there. So the same one right here. I can start out immediately seeing this as a 1 over. So in our experience that we've seen from part A and B, this square root of x cubed is the same as x to the 3/2 power. I can put that in the denominator right there. So we start seeing power being displayed. And then from here, I see this as a reciprocal. So now I see in the next step, I see it immediately will become x to the 3/2 power, take the reciprocal. Similar argument as how I was doing this. It's just a different order. Okay, and then see now these two together in the end, it's just exactly the same. So this will land into that exact form. It's a different way of arguing it. All right. And now even more as experience, just even more as experience. This same problem. And now I hope viewers are done with this extra blue note right here. Allow me to erase that because the main core of the problem is still here. At calculus courses, you may even see function as written as following. The same expression. The exact same function, but maybe algebraically written in the following equivalent expression. I'm talking about the same function. Maybe written as 1 over, how about x times square root of x? Because think about it. This is in root form at start, but it was not reduced. So a lot of times, or quite sometimes, you may be given a function where it's in a form of a 1 over, okay, but in reduced form. All right, 1 over in reduced form. Ladies and gentlemen, I want you to use your own algebra from the prerequisite course to verify how these two are the same. Well, they already have the same numerator 1, but how is this square root of x cubed the same with the x times square root of x? You can verify that on your own right there. Okay, but now how I see that, see, all that here will be the same as x to the minus 3/2 power x to the power negative 3/2. All right, and so, but the part that we go from square root of x cubed, and how you can see that the relationship between square root of x cubed and the x square root of x, I want to leave that for anyone viewing this video to verify that on your own, because that is part of your learning from the prerequisite course. You can pause the video and take a piece of paper and do the math on that. Just focus on this part and see how they are the same. And once you're convinced that they are the same, then if this one here lands into that, then of course I can skip all those steps and land this function exactly into that form where we have expressed that as a power function. All right, so that's another function, another problem where, see, so now all of a sudden we realize the power function is such a big, larger family or class of functions out there. Too large. A lot of our functions that we have seen in our past courses is one member of this class of power functions. Okay, let's keep working a little further. All right, so part D. Initially, I didn't plan to bring in this, but in case anyone didn't build enough experience from your prerequisite course, I'm not saying that you haven't seen these kind of operations, but now it's just a matter of, I introduce again these kind of problems you have seen in your past course, but now I trigger your experience. how you can put these details you've learned from your past course together, and then we put that in a pre-calculus course here. So what about f of x? All right, equals f of x equals, so here we have how about 1 over, okay, and now let's just stay with a, how about cube root of x. Now I'm going to raise that. Now cube root of x is inside a power here, raising this to power 4th, for example. Okay, 1 over cube root of x to the 4th power. Okay, completely at start, we have no clue how this is a power function, but now here's how and like I said, in your prerequisite course, you have been introduced to cube root of x function. You have been introduced to at least understanding how to operate with cube root of x and then being raised overall to a 4th power. At least you've been familiar with that. And now we're going to bring all of that experience into a higher level for here. Okay, so this is how I'm seeing it. Reciprocal is brought, is turned into, is re-expressed, is identified as, and it's a reciprocal, and down in the bottom it's a 4th power. So similar to that toolkit's function 1 over x squared. Okay, 1 over a power, then I can write it as an x to the negative 2 power. So 1 over a power, disregarding completely what's inside of that power, but see 1 over a power. So I take that experience here. So you've seen all of this experience. Like I said, all of your prerequisite course, the learning exists here, but now new experience for us. So now it's going to be cube root of x to the negative 4 power. All right, we're close. And now from that experience we've seen earlier, from cube root function can be thought of as, and when I was explaining that about those toolkits function, a couple of the toolkit functions I brought up right here, then cube root of x is the same as x to the 1/3 power. But see, x to the 1/3 power for now stays inside of a negative 4 power. All right, and so again, you must have seen from your, and see any of these skills I brought in here, they're all from your prerequisite course. So if you feel unsure about these skills, I highly recommend that you review your prerequisite course right there. Okay, and then now from your learning from prerequisite course, then you see we multiply these two. It's a power inside of another power, a power being raised to another power. So now we're going to multiply the two powers here together. So 1/3 times negative 4, it's x to the negative 4/3. This is one way of seeing it. But now at least I have re-expressed, I have identified this function at start, or I have recognized that same function at start as a power function. One input variable raised to the power negative 4/3. All right, so like I said, you have seen all of these operations from your prerequisite course, but how we argue it and bring that into a final power form, this is where pre-calculus is. Okay, and so now your calculus course later, and this is the reason why this class you're learning right now is called pre-calculus, because it preps you for all of those skills that extremely vital, so that when you see them a lot in your calculus courses, you won't shock. It's all the algebra, but we put the algebras in an experience, in the kind of experience that preps you for calculus. All right, so that's a power function. Okay, we see that as a power function, and just like that earlier problem I brought up allowed me to show a different way. So right now it's just one way of how I organize my thoughts, how I organize my reasoning to recognize this as a power function. You can also see this as a 1 over, okay, and then immediately inside the root I have an x to the 1/3 power and raise that to the 4th power. So we can go in that route of organizing the steps right here. Okay, so it's just a different ways of organizing the steps. And so now I still keep that in the reciprocal form, but now I'm seeing this as a, so you see in the denominator here, as far as combined power, this is x to the 4/3 power. All right, and now I'm recognizing this as a reciprocal. Now we can rewrite that as all of that here, just simply now currently positive power, I put that as a negative power. All right, so throughout this, the whole point and my other intention of this example bringing up here, it's yes, it's a one directly relevant problem to the material we're learning right now. And my intention for this kind of example is that we can see that the power in our power function does not have to be whole number only. Okay? Now, at least we're done with example 1. So let me erase this and readdress what I was saying just now. All right, so at this point, yes, anytime we have our function is in the form of x to a power p, f of x equals the inputs raised to a power. Now I have to emphasize, when I brought up x or an x squared and x cubed, and then I took a pause there, and then I moved on to introducing the power function. I made some people think that the power has to be positive number and whole number. Positive number and whole number. But nope, throughout example 1, and as I have already mentioned here, the power does not have to be positive or negative number. I mean, it can just be any number. Really, it can just be any number. It doesn't even have to be whole numbers like this. This is the case where it's nice, whole numbers. Easy to work with those powers. But here, the power function, be ready for your calculus course later on. Power function can also involve you see, fraction powers, but still positive, and the negative powers. And even throughout our examples that we've done, we've had negative and fraction powers. We have numbers all over. All right, so now with this, now I can just make a little remark right here. So P is simply any number, okay? Any number. Highlight that for me, and I will get back and really make it clear here. P, the power can just be any number. And right now, I'm not talking about domains or anything like that, okay? And so in that way, for our beginning of the journey here, you already learned just now, power function is such a large family of functions out there, okay? And especially now, I just emphasize that the power P can just be any number, and we've seen that throughout all of the entire example 1 so far. Then we have a lot of functions being members of this class of functions, the power function. Okay, so now particularly I would like to turn our focus, okay? Because in the end, initially this lesson is planned so that you've learned about power function, and we make that as a lead into learning about the polynomials, And so now after this example 1, allow me to start focus. So right now, we're gonna only turn our focus to those power functions. We're going to turn our focus to those power functions where P is positive. All right. And so this is an important turning point of our learning right here. Because as a matter of fact, power functions have a lot of different ways, right? But now we particularly turn our focus to the power functions, to those members of the power functions where the power is positive, okay, and is a whole value. All right, positive and whole value. That's what we want to focus to. So from this turning point of our path, because once we are fluent with these, we should be able to drive to make a smooth transition into the polynomials. And so that means back to this list of those power functions that I brought up, they were from our toolkits functions, but now we're not going to focus on these. We're not going to worry on these because right now our current focus, we focus to these guys right here. Positive power and whole number. Power 1, power 2, power 3. Power 5, later on we will work with power 9, power 4, power 6. X to the 6th, x to the 4th, x to the 9th, x to the 7th. Okay, those are the ones that we particularly want to focus to. All right. All right, so these are the ones. All right, positive powers and whole values. And so for some other quick little examples. See, I didn't number my example here. It's just meant to be something I brought up as demonstration. X to the 9th, okay. F of x equals x to the 4th. F of x equals x to the 8th, okay. And f of x equals x to the 5th. We have so many of those guys out there. All right, so now as far as this point, then yes, the rule, and once we've seen these functions, once we have these functions given at us, then it just means it's a rule. This function is a rule, that function is a rule, that function is a rule. The rule says we raise whatever inputs to the given power, to the power given. And so if it's x to the 9th, admittedly, it probably doesn't happen to our work that often, but I just want to let you know, power 9 exists out there. There will be times where in your application you need to raise an input to the 9th power and continue doing that for other values. And that's why x to the 9th as a power function exists out there. Even though right now at our level we're just beginning into this family of power functions, we don't see that kind of function that often. Okay, so f of x equals x to the 9th. The rule says whatever input, we're going to raise that to the 9th power. Okay, this function f of x equals x to the 4th. At this level right here, somebody must have seen this. Somebody may have not worked with that often enough, but it exists out there. Any of these functions here, they're all power functions, positive powers, and whole value power being whole value. So you already know those are functions. It's not anything worth our time to keep repeating what they are. Okay, now I'm going to get straight into learning about their graphical behavior of these things, because the fascinating things about these power functions, okay, like I said, the one fascinating feature with power functions is that when we're looking at their graphical behavior, but for now, because we're learning about these power functions as a stepping stone to lead our understanding into polynomials, which will come later in this same lecture right here, so allow me to focus on x to the p, where the power function here is, the power is positive and whole value. And then now we're only going to study the graphical behavior of these power functions where the power satisfies us. Positive power and whole value. Positive power and whole value power. Okay, so let's get to them. Let's get to them. All right, so now we know where our focus is. All right, so now allow me to bring in my graphing screen right here to be blended into this particular screen right here, because I want to show the function and I want to also show the graph. Okay, so let's observe the graph here. So, but see, before I even get further, how about let's look at something. Among those, because right now we work with x to the p, and now yes, p is positive. Okay, p is positive and p is a whole value. Okay. Whole value. So p is positive, of course they are, but p being whole value, there are two cases. There's even whole value and there is odd whole value. Like odd, like a 3, a 5, or 9, or 7, 11, 13. Evens like 2, 4, 6, 8. And odd power also means x to the first power. Okay, so let's take a look at them. All right, so in that way, and I pointed out that nature just because we're working with the power being whole value. We already expect that there will be two separate classes of powers, even powers and the odd powers. Okay, and so now be aware of that, and I will bring it in. I will bring it in. But for now, let's focus on those x squared. Okay, x to the 4th, x to the 6th. Okay, and then there will be many more, like x to the 10th, x to the 12, x to the 14, the 16th, and any even power. Yes, so my aim right now is to focus on the even power. Even power. All right, even power. So now it bothers me a little bit to skip that I skipped this f of x notation. All right, so forgive me on that. So now let's bring up the graphs. All right, so this is my empty graphing space right now. The x squared function is here. We have seen that before when I was introducing about and when we were studying about the toolkit functions. That nice parabolic shape like that, that nice parabola is our graph for the simple quadratic function. Okay, so x to the fourth. Now, just for you to know, this is not requirement, but fourth power, this simple fourth power right here is regarded as, this is a quartic, okay? A quartic. So quadratic, we already know, quartic, power 4, okay? Quartic. All right, and then yes, it's just x to the fourth, and no special coefficient in front, and we will get to that. All right, so quartic. So here I call that simple quartic. And then there's no need to have a name for the 6 or even later. Okay, so now, so the x squared is there. Let me now bring in the x to the fourth on the graph. All right, so this one here is the x to the fourth. Okay, let me now hide away the x squared. So it looks just like the x squared, but now allow me to zoom in the bottom part where this graph is sitting at. Okay, where the graph is sitting at. This is x to the fourth. Now let me hide x to the fourth away and bring back x squared. So they're all having that vertex down here, but what's the difference we have already observed? The x to the fourth looks just like the x squared, but more flat now at that bottom peak right there. Okay, at that bottom, now formally we call it's a vertex. Okay, but like I said, I like using the term in some of the earlier lessons when I talked about graphs. Even people would call that the peaks and valleys, but I see valleys also as bottom peaks. Right there. So in general, I just see them peaks. They peaks away from a certain the zone right there. Okay, so this bottom peak right here, or this low peak, okay, it's more flat out, so it comes closer to the x-axis. It's still only going to meet, this graph right here is still only going to meet the x-axis at one point, because if we keep, see right now, the graphing utility I'm using here fails to show the difference between the graph in red and the x-axis in a certain zone, but actually as we keep zooming in, we will notice the difference, some difference, as we're zooming in close enough. You see what I'm talking about like that. All right, so now, but there's no need to keep hunting into those the infinitesimally small thing right there. All right, so x to the fourth, it's just now as a general shape, it's more flat out, right, at the bottom seat compared to the x squared. But they all have this shape right here going up on the two ends. I'm starting to blend you into that understanding. They are both rising up on the two ends right there. Okay, let's continue. So this is x squared. That was x to the fourth. And so now let's observe x to the sixth right here that I have on the screen here, that I wrote on my board right here. All right, so this right here, observe the graph. This is x to the sixth. It looks almost identical to x to the fourth. Allow me to bring in x to the fourth in a different color. How about in blue right here for x to the fourth? Because, all right, so x to the fourth is the blue and x to the sixth is the red right now. All right, and now let me bring back x squared right there, but keep that in green color. How's that? Okay, so x squared is green, x to the fourth is blue, and x to the sixth is the red currently. And they all having that primary shape right here. Both ends rise up. Right end going up, left end going up as well. Okay, that's x to the sixth. And so the bottom seat's even more flatter, even flatter out. More flatter compared to the x to the fourth. Okay, and so that's our observation on that was our observation on the even power. Those are power functions where the power was even. And then we'll put all of those observations into a formal understanding about the graphical behavior of these. All right, or if you would like to make a hand sketch note right here at this point, you're more than welcome to do that. You see, I can just start closing my eyes and advise myself that the graph of any of these is the shape where whatever at the bottom here, but left end and right end, they're going up like that. Left end and right end. Okay, left end and right end. All right, and so now let's turn our attention over to the odd power. Okay. All right, so now as far as the odd power, primarily going to be looking at x to the first power, the identity function, one among our toolkit functions. How about f of x here equals x cubed? These are the only two odd power functions, right, among our toolkit functions. But how about here? You may have seen it before, you may have not, but it's one of those, x to the fifth. Okay, f of x equals x, f of x equals x cubed. We know that this is the identity function. This is the simple cubic, that's how I call that. And this is now, so for you to know, just for you to know, it's not a requirement. Okay, this x to the fifth right here is called, it's a simple quintic. All right, it's a simple quintic right here. Okay, so at any random day you walk into a math department and you saw a poster that say there are people who study about a quintic, or the behavior of a quintic. You know what that means. They're talking about a function, at least we know it's raised to the fifth power. All right, which is something kind of outside the lecture here for you to know. All right, so now let's again look at their graphing behavior. Okay, so now I'm going to bring back the graphing screen here. And as a matter of fact, let's keep that as a corner of our board right here. So with the empty graphing space now, allow me to center the axes here, because these graphs have some good fascinating feature that you definitely want to keep the screen here as complete as possible. So f of x equals x. What's this? 45-degree line, but notice it goes straight and it went through the origin. All right. Now, allow me to brief back on one of the even functions a little bit. Okay, this was the x squared. The x squared, or the x to the fourth, or the x to the sixth, none of those has a negative part, meaning a part that sinks below the x-axis. Okay, none of those even powers have a part of the graph sinking below the x-axis, because it's just the way it is. Even powers for whatever inputs, even if we put in a negative input, it's all going to get it positive for the outputs. And that's why, this graph right here for x squared, and the same thing for x to the fourth, and the same thing for x to the sixth, the graphs looked entirely above the x-axis. Both ends, and we will get even further into that. But now back to the odd function. It's just the way the odd power is. And I shouldn't even say odd function. I should be saying the odd power function right here. The some part is negative, some part of the graph sinks below the x-axis, some part of the graph stays above the x-axis, and it went through the origin. Okay, it went through the origin, right through the origin, as you can see on the screen right now. Okay, so now how about, let me hide away this f of x equals x. So this one right now you are seeing is for that function, f of x equals x. Okay, you can pause the video and take a quick sketch again, and I believe you don't have to because you already have seen this quite often. Let me now put away f of x equals x and put in f of x equals x cubed. This is the one. And again, back in the days, back in that lecture where I introduced the toolkit functions, you must have seen the graph of this one as well. It looks like a waterfall, but here's one common thing that it has with the f of x equals x right here with power of 1. This is power 3. This is the f of x equals x cubed, that simple cubic function. Okay? F of x equals x cubed and f of x equals x that we've seen earlier, they both going right through that origin. And one more thing there is in similar, even though now this curve here is a lot more bent compared to f of x equals x. F of x equals x is one straight line going up, and going through it was going through that origin, like right here. Okay, but now allow me, this was old one, so I'll bring it into how about a green color. Okay, but the one we want to particularly compare now is the x cubed. All right, so it's still one side down, one side below the x-axis, one side above the x-axis, and then see this graph in red also goes right through that origin. Okay, all right, so that's x cubed. The one we have here, that's x cubed. Okay, and so now let's hide away. All right, so now let's look at x to the fifth. So this now I just brought up is that function for the simple quartic, the simple quintic right here. Okay, quartic is for the fourth power. I apologize for momentarily using the wrong term here. So this is the simple quintic. All right, fifth power, power 5, odd power, okay, positive power, and the graph looks, gosh, it looks just like that graph for x cubed. So x to the first power was a nice straight line going through that origin, right through the origin, one part below the x-axis, the opposite part going on the positive axis, but here, the positive above the x-axis. But now x cubed and x to the fifth here all look the same, pretty much, except for x to the fifth is more flat out. It's more flat out right here. Okay, it's more flattened out near the x equals 0, near the origin, near where it's seated, compared to so now the version in blue right here is the x cubed. They look almost matching with each other. Okay, from a far zoom, they look almost no difference in some certain zone. All right, and so now we start drawing some generality about these odd power function. All right, so for these odd power functions, then one common characteristics, as a quick note right here, I see that the left end, okay, goes down like that, and the right end goes up like that. This straight 45-degree line is our f of x equals x function. And then when we come to the cube, see one side, see the positive side here, the side that's to the right-hand side of the y-axis, that's what I call the positive side, also stay positive. The same with the x. And then the x cubed right here, see, and now when we're letting go of scales, I can't even tell between, is this x cubed or x to the fifth? It's not even important. It's just primarily it's the shape. This end points up, this other end, left end points down, the negative end points down. And we didn't formally get into the end behavior yet, but I start letting you realize that nature right here. So this is everything we're learning about odd power, and you can see that they go opposite ends on the two ends right here. They go opposite direction. All right. So fifth power maybe even more flat out and more rapidly rising, more flat out and more rapidly falling. Okay, and then honestly, I cannot even tell if this is an x to the fifth or x to the seventh or even x to the ninth. But see, the higher the power is, the more flattened out it is at that origin where it's passing through right there. And that's the whole idea about these odd power function. Okay, and so now, after we have seen enough, yes, let's look a little further before we're gonna make a generalization. Okay, so I still want to keep the empty graphing space here, so let's pop it in. All right, so now let's advance our understanding a little further. So how about let me pick a random power function, x to the fourth, okay, and a random selection on an odd power function, x to the 7, okay. And so just these on its own in the most simplest form. This one here, I am expecting that the graph is doing this on the right end, and this graph is doing that on the left end. It has to be, okay? Just like that. This is truthfully the graph for x to the fourth. Okay, just like the picture I'm drawing here. All right, and now what about this odd power right here? I must be expecting in my mind, in my imagination, that in this way right here, right end goes up, left end goes the opposite way. I'm expecting a shape like that. Okay, so let's see if it's true. All right, x to the 7 is right here, almost identical to the x to the 5th. Okay, right end points up, left end points the opposite way. Right end points up and left end points the opposite way. But so I'm not intending to repeat what we have already learned. Let's look at something like this. All right, so now I'm going to erase the graph right here. All right, this is what I want to look at. So it's really and formally the study about those power functions with odd or even power already stops wherever right before this point. But now, of course, we have to advance our understanding in terms of bringing in more details. I'm talking about bringing in more details into these power functions. Because otherwise, what else is fascinating about these? Okay, because right now we only focus on those simple terms. Okay, but now what about a 3x to the 4th? I introduce a coefficient. See, I introduce a constant that's multiplied to our power function. So the power function is still here, the x to the 4th. But now I just simply introduced a constant that's multiplied with that power function. So same thing here. And it doesn't have to be a whole value like that. We can go with fraction or anything like that. And right now I stay with a positive number, like a positive 3. I multiply as a constant. I multiply with that 4th power. I mean with that 4th power function. What about here? I'm multiplying a 4/5, positive 4/5 as a constant. Multiply with x to the 7. Okay, so sooner or later you will learn that term. So now allow me to introduce, and we will set forth for that into that understanding formally later on. But this constant that I multiply with our power function, it's a power function, and we multiply with a constant. It's a power function here, and we multiply with that constant. So multiplying the constant to the power function here, I call any of these, so the 4/5 or the 3 over here, formally they are regarded as coefficient. So we have a coefficient in front. Okay, we have a coefficient. It's just, so what exactly is a coefficient? And you must have also learned this term from your previous course, but here at this level, when we study formally about polynomial, and especially we're starting out with power function, it's now time to learn that formally. Coefficient is simply just a constant that we multiply to a power. A constant that we multiply to a power function. A power function. Okay, a constant value that we multiply to a power function. So here I have a coefficient positive 3. Here I have a coefficient 4/5. Coefficient does not have to be whole value only. Okay, and so in other case, the same x to the 4th, the same power function. And like I said, this x to the 4th I selected out of as a random selection. But I can also multiply with a negative 1/2, a negative coefficient. And then x to the 7 here, I can multiply that with a negative 2. Negative coefficients, multiply with that. Yes, let's find out what happens. But in the end, see, this is a coefficient. That 3 is a coefficient. That 4/5 is a coefficient. These are all positive coefficients. And these, see this one right here that I circle, it's a negative coefficient. But it's a coefficient. It's a negative coefficient here, but it's a coefficient. So just that whatever constant value that's multiplied in front of our power function. Okay, that is, we call any of those the coefficient. Coefficient. All right, so now on my graphing space right here, let me bring back the graphing space. How about let me bring it in the full screen view right here. All right, so in full screen view, and allow me to zoom it out a little further out. Okay, so x to the 4th, I already had some expectation in mind. The shape is like that. Okay, so now if we multiply with a constant coefficient, or just simply a coefficient being a positive 3, then here's what's going to change it. All right, so it's gonna make the graph even more scaled up. And so, just as I said in the beginning of this lecture right here, it is beneficial that we're studying this after we have learned some transformations, because if we multiply a coefficient in front of the function, we can think of that as it's a vertical scaling. In my terminologies, if I would explain about the concept of transformation. Okay, but if you've learned that prior to this lesson or not, it's not too important. The idea is it's still gonna carry that same, or primarily, it's still gonna carry that same fundamental with the simple x to the fourth. Both sides are rising up, as you are still seeing that here on the screen. Okay, so without a coefficient. And by the way, so now the one I introduced earlier, just x to the fourth, and I shouldn't even say without, but so now without seeing a coefficient here, there is still a coefficient. So now when I start introducing about coefficient, I have to get it real clear down, okay, and tear it down to every crystal clear detail right here. Yes, here we see a clear coefficient, but here we don't see a coefficient clearly displayed here. It means this coefficient here is coefficient 1 officially. Okay, coefficient 1, this is coefficient 3. So any power function naturally comes with a coefficient 1, or by default comes with a coefficient 1. Let's say x to the 7 by itself, it seems like we have no coefficient. But nope, it's not that. It's not that we don't have a coefficient, it was coefficient 1, so we didn't have to write it. But now when coefficient is something else other than 1, then we have to write it out. So this is coefficient 4/5 right here. Okay, but something like that, it means coefficient 1. Just something like this, without a clearly seen coefficient, it means coefficient 1. Now I got to really tear it down right there to, crystal clear detail. So now, again, back to the graphing mode right here. Okay, and now let me bring the graph and just let me put the graph at only a one corner right here. So this graph is 3x to the 4th. Okay, coefficient 3, compared to that version where it's just coefficient 1. All right, so they still carry that same shape of rising up. Okay, so rising up is both sides rising up. So it looks like what matters is the even power is making it rising. I mean, both ends rising up. Okay, so rising up, both ends. But let's hold it. Okay, let's hold it. Now, right now, I'm currently working with x to the 4th. Generally as an even power. So let's switch over to how about a negative coefficient. So on my board here, I also listed down how about negative 1/2 x to the 4th. So positive coefficient, it stays the same with the coefficient 1, both ends rising up. Okay, but now what if we have negative 1/2 x to the 4th is here, ladies and gentlemen. All right, and so this time, what have we recognized here? What has just happened to our graph? The whole shape there, it's still being seated at that origin, but the whole shape flipped upside down. So again, I said earlier in the lecture here, it is beneficial that we've learned this lesson here after you've learned about transformation, but it's not too important about that, okay? Because having a negative in front of our function is going to flip our function upside down. So with this negative coefficient here, but in the end, fundamentally, the two ends, even though they're now pointing down completely, but both ends are pointing in the same direction. Both ends are pointing in the same direction. See, left end and the right end. Look right on the graphic that you're still seeing left end and right end, they both pointing down. All right, whereas in case of a positive coefficient, like we've seen earlier, positive 3, both ends are pointing up. So now we can have a generality for our as a conclusion. So coefficient does make it different a little bit, but in the end, that same generality that still remains is that when it's even power, okay, both ends of the graph point in the same direction. Both ends of the graph point in the same direction. Okay, And so now we will put all of that details together. But now I start leading viewers and students of mine further into talking about the ends of the graph right here, the right end and the left end. Okay? Let's look at this. So now let's focus on our odd power function. I used power 7 here randomly as a selection, okay, as a random selection. But it should generalize all of those odd power functions out there. So you have already seen x to the 7, okay, graphically. And let me bring up the graph. All right, in complete full view, x to the 7th is here. All right. And now, but that function right there is just the simple x to the 7, coefficient 1. But now let me introduce a positive coefficient other than 1. How about a 4/5, like what I have here on the board? So now I'm going to change my function to a 4/5. And now the graph still is the same. The graph still looks pretty much the same unless we really have to dive in and see how much it's changed. But in the end, same fundamental shape compared to the original x to the 7th coefficient 1 here. All right, and so now let's speed up the process a little bit. I'm going to switch that to how about a negative coefficient. All right, so how about in complete full screen view? Here's a -2. There we go. All right, so this time, what just happened? Now when we so these two have the same shape. Now this case right here, the shape got flipped completely upside down through the x-axis. Okay, so like I said, if you've already had some understanding about the transformations, use your understanding from transformations will apply here. Okay, but in case you haven't learned that, that's completely okay. Now the main thing I want you to keep in mind, it's all due to the fact that it's negative, it's flipped upside down, but now in the end it still have one generality with all of these odd ones. The two ends go opposite way. So let's classify that a little bit by what I meant by two ends go opposite way. X to the 7th or 4/5 x to the 7th, positive coefficients. Then right end goes up, left end goes down. That's what it means by two ends go opposite way. And then in this case right here, whatever in the middle, I didn't mention that, I didn't even pay attention to that, but right, because the graph flips due to that negative sign. So right end points down, left end goes up, but in the end, two ends, it's still holding the same truth here. Two ends go in the opposite way. That's generally what happened to an odd power function. All right, so in this way right here, now I introduce for you, I've been looking at the ends of the graph, the right end and the left end. All right, so ladies and gentlemen, now allow me to use a formal term here. I was looking at right end and left end. So generally, any of those that we just now looked at, and it went completely graphical. So any of those behaviors I was looking at, we refer to them as, now many textbooks, allow me to stick with the term that many textbooks use, a good majority of textbooks use, and behaviors. Okay, and behaviors. Okay, of a power function x to the power p. And behaviors. So what exactly does that mean by and behaviors? We want to study how the function behaves, how a function behaves as its go to the right end on its right end vertically. Okay, is it vertically dropping as the function approaching the right end, or is it vertically rising as the function approaching the left end? Okay, and that's what I meant by and behaviors. How is the function behaving on the right end, and how is the function behaving as we are approaching further to the left end? As we are tending to the right end, how is the function behave? And now I have to also mention vertically behave. Okay, So now and behavior, it breaks down to, you know, there's also left and, okay, and right, left and right and, okay, behavior. There are two separate behaviors. So together we call them, it's the and behaviors, okay? And that's what the majority of textbooks out there use as a term, as a term. However, there are quite also, you know, there are quite also a few, there are quite also some noticeable number of textbooks also use a term. So and behaviors, a good number of professors and textbook authors also use the term long run, okay? Long run behaviors. Okay, it's the same meaning. So long run, it's just and behavior. Because you see, to get to the right end, we have to run really long, and we keep running, right, to the right hand side. That's why it's called a long run. And then the same way to get to the left end of the graph, okay, we're going to have to keep running long, infinitely long. That's why many professors also use the term long run instead of and behaviors. All right, so admittedly the term and behaviors is used a lot more throughout textbooks, but then in these days I also noticed that quite a few professors and textbooks authors use the term long run behaviors. These two are the same. Allow me to stick with that name more formally, because that's how it was introduced from my first days. Okay, but it should be the same thing. All right, and so now, and I will also introduce some other symbols and notation as we go along as well. But now at least we have had the following, we can generalize the following understanding. And so all of that, I don't need to go too far into the wording, but so now on any polynomial, I mean on any power function, okay? And then I should have written this even x to the p, but with a coefficient. X to the p with a coefficient. All right. And so now we can generalize all of our observations earlier when I pointed it out through the graphs. We can put things into the following table. We can organize things into the following table. So what matters really is about, what changes is whether our power function is odd power, okay, odd power or even power. That's what I'm saying in my chart right here, odd p or even p, because p is a power. Okay, and then we have seen earlier, I've walked you through with the 4 different cases right here. What matters is the coefficient is positive or is a negative coefficient. All right, and so now, so in that way, graphically speaking, when it's odd power, see, right end and left end goes opposite direction. For clear, right end and left end goes opposite direction. But when that coefficient in front of your power function is a positive coefficient, then right end points up and left end points down. And whatever happens in the middle, that's not what we're looking at right now. So I'm leaving dots here, but see, because right now we're looking at and behaviors. So right end points up, left end points down, and that means generally as a characteristic, when it's odd power in our power function a times x to the p right here, then left and right ends point in different or in opposite directions. All right, and so similarly, now it's opposite direction as well, because it's still odd power, but now when our coefficient in front of the power function switch to negative, then the left end points up. So if we keep approaching, if we keep heading out, if we keep tending out to the left end of our function, then it's rising up vertically. And then as we tending out to the right end, the right end points down, but in the end the two ends point in opposite direction. All right, and so now in that same way, we have seen that earlier when it's even power, okay, right end and left end will point in the same direction, one direction. So when the coefficient is positive, then both ends, right end pointing up, whatever in the middle, that's not what we're looking at. That's why I don't know, I'm leaving dots here. But now left end I know for sure as an expectation, have to both going up, because both ends are pointing in the same direction. Okay, and then when the coefficient in front of our power function, in the case where it's even power, when that coefficient is negative, then whatever in the middle, that's not what we're looking at. We're looking at left end and right end both pointing down in the same direction, like that. So this is a fundamental, this is the building block for our understanding later. Okay, we starting to learn to look at and behaviors when we already arrive at our power functions understanding. Okay, so now along the way, some textbooks introduce this, some textbooks don't, but allow me to introduce this. I belong to the groups of authors or the professor who want to teach this a little early. Okay, so now let me get on this side of my board here. All right, so because we are currently talking about and behaviors, specifically, I mentioned that earlier, there's left end and right end. You see, and I was using, so for example, something like this. Okay, left end and right end refer to the understanding that how the function behaves vertically. Again, and behavior means how the function, we want to describe how the function behaves vertically. Is it going up or is it going down vertically? As we are tending to the right end, and you can see that I'm using my finger and point to the right hand side. And so now, just a notation, it's only a symbol, and you will get it tear down in a real clear detail at your calculus course. But now, right end behavior, okay? Right end behavior. First of all, we use this symbol x to, see, x is getting to, that arrow, x arrow, positive infinity. So right end right here is indicating x is getting to, that's what the arrow is pointing to, x is getting to positive infinity. Because see, this is positive infinity on our x-axis. So as we keep letting x values going to positive infinity, getting further and further out to positive infinity, what is the behavior of our function vertically? So in the case where I'm drawing like this, the graph is rising up. And so together we're saying, together as, in this case, as x is getting to that, okay, then the y value, see, vertically, as x is getting to the right end right here, y value is rising. So I'm also using the arrow symbol, but I'm talking about the vertical direction now. In this case right here, y value goes to positive infinity. Okay, and this concept right here you will investigate very intensively in calculus. Here it's just like I said, we're only at a pre-calculus, we're only giving it a preview. But it's easy enough to understand right now. As we see, so this symbol means right end, and then that is the behavior. This is the behavior. So that's why as we getting to the right end, should I put a comma to make it like an actual grammatical sentence right there. As our x values tending to positive infinity, or generally as we're getting further and further to the right end, that's what it is. Then our function behaves in a way that the vertical values, in this case right here, going up. So it could be going up, it could be going down. And so same way right here, now the symbol I want to focus is that symbol, the x arrow. That's indicating right end or left end behavior that we're studying. So now in this case, if we're reading this graph right here, this is called, we're looking at the left end, okay, the left end behavior. Okay, so now in that same way, now we have learned long time ago that going to the left end means it's a negative infinity side is here. So that means as far as the x value, we're letting our x values goes to or tending to negative infinity. So I'm using that arrow symbol again. So here's as a complete statement, as our x values tending to negative infinity, left hand. For this graph here particularly, our y value drops vertically down to negative infinity. See, this is the behavior. Our function behaves in a way that it drops down vertically, keep dropping vertically as we're tending to the left end and left end. And that's why now in these days a lot of professors call that the long run behavior, because see, running to infinity, negative infinity or positive infinity, in the end it's indicating we run a very long distance, infinitely long. And that's why many authors and professors refer to that as long run, even though I believe the more the classical way of saying that is the end behavior. I never did an actual historical search on which word is more original, like the long run or the end behavior term. Okay, and so after bringing up the arrow notation concept, then now you can see in a graph like this, right end and left end, you can formally state it as a word here that, and I have to write it small. Okay, so as x goes to positive infinity in the shape like this, right? Then y goes to positive infinity, and then here as x goes to negative infinity, y value goes to negative infinity. That's what's happening in this graph right here. All right, and then you can spend your time filling out the rest of this in the table. See, for example, here you can say as x is tending to positive infinity, all right, and the y value is also approaching positive infinity, if we want to explain that using symbols and notation as a complete statement. And then here, that piece right here saying as x is approaching negative infinity, then our y value is still approaching positive infinity. All right. And so similarly down here in this right piece right here, see, as x goes to positive infinity, our function our y value drops to negative. That's why I have that symbol here, negative infinity. And then here I can say as x approaches negative infinity. Negative infinity, okay? Our y value is rising to positive infinity. It's that direction. All right, and then similarly, now you can see where I'm going right here, as much as details here. So in this way, how the graph is looking, as x approaches positive infinity, okay? Right end is always x arrow positive infinity. See, right end x arrow positive infinity. So here I'm looking at how about y is approaching negative infinity. The y value vertically drops. The graph vertically drops. That's why the arrow is pointing down as well. All right, and so now, and then same way right here, as x approaches negative infinity, y value approaches negative infinity as well. See, so going in the same direction right there, left and right going in the same directions, pointing down. Left and right going the same direction, pointing up. That's when p is even. All right. All right, so now at this point, we are ready for example 2, which is directly relevant to what we've learned here about the end behaviors of our power functions. Okay, so now for example 2, allow me to put the wording instruction of the example on the computer. So I changed style a little bit. So instead of writing down the wording instruction for this example 2, even though it's an example where it's still directly relevant to the material we're learning about and behaviors, but allow me to bring up a computerized program that generates these problems. Because when it gets to these, when it gets to studying about long behavior, it's all about we're expected to make a quick judgment. Okay, we want to expect a quick judgment. So there's no reason to keep writing it down. So I'm going to save all of that worded instructions on the actual picture on the computer screen right here. Okay, and part A, part B, and part C, we can do tons of those problems right on the computer screen. Okay. All right, so right now, this is my computerized version of the example 2 over here. So you can see that the general description of the problem is right here. We want to describe the long run behavior. So here I'm using that term where some textbooks authors using it long run behavior, but it really means the end behavior. Okay, so long run behavior is the same as end behavior. So the function in part A is this: f of x equals negative 9/2 x to the 6. So we have a power function x to the 6 here, and that coefficient is a negative 9/2. So now I want to see, so this is the symbol for right end. So we want to study what that right end behavior is and what that left end behavior is. See, how will the function, this is y value. So how will y value behave? Is it going to positive infinity or negative infinity as we're getting to the left end or as we're getting to the right end? Just like how I was explaining it with this board. So now we're going to use this board to describe, okay? And so I'm going to write part A down in the other board. Okay, so the worded instruction was already given on the computer. So it was to describe the long run behavior. Describe the long run, okay, behavior. Okay, and so now in part A right here, the function we have really is negative 9/2 x to the 6. Okay, so that's the function, and it's only meant to be a quick, short answer as soon as we're seeing that. So on the chart, I'm seeing the function was was even power. That power was power 6. Okay. Even power 6 right here. So immediately I am expecting that we're in this column about the long run behavior. So both ends have to point in the same direction. That's already in my expectation. So now what matters next is the coefficient, negative or positive. Okay, if it's negative, it's this case right here, both ends pointing down, and then if it's positive, both ends pointing up. And I also have that those notation or symbolic expression here. There's the graphical interpretation and there's the symbolic expression there. All right, so the answer is all decided here. All right, so now we are in that particular problem itself. Okay, so now coefficient negative. Okay, the function itself is positive. The function itself is even power. And so now as x is going to the right end, right, at the right end behavior right here, the function will rise to, all right, so we have, now I will indicate we will have negative infinity, okay? And so with this software of mine, since I'm the instructor, I have the version where it will show the key, and so I just want to show you that our selection here will be correct. Yes, and that will be correct. Okay, and so just like that, now on the left end right here, as the left end behavior, well, let's see what our function will behave like. It should be to negative as well, because it's even power, so both ends behave the same way, going in the same direction. That's why I have both negative infinity, and that is consistent with the answer that the software already had in mind. All right, and so that's how we answer a problem like that. All right, so now we're gonna get, once you understand the idea of what to do, and especially how we can provide an answer to an online assignment, and many online, whatever the version I'm using of the online program right here, it's not the only one. I believe there are WebAssign for students in the state of Washington. There are YMAP, and there are many other web assignments offered throughout the entire nation right there. But they all have the same way of working. Okay, and so let's look at the next problem. All right, so now we can call this part B right here. So what our function here, wow, again, and it's this time I really made and the advantage of using a software to teach math in these modern days, that we have the software has the capability to randomize our problems. So now we are given a different problem as part B of the example. So now we're still looking at a power function being fourth power. Fourth power is here, okay? and now that's it has a positive coefficient this time. All right, so let's just write it down first. So now as far as writing it down right here, now our part B of the function. And so, and needless to say, since I'm working interactively with the computer screen, I expect that you can roll back to the video and write down your answers to the note if you want, if you would like to, but make sure you document your work if you're learning directly from this video right here. Okay, so part B, our function here is positive 7/4, okay, times x to the 4th. And so like I said, I will explain, I will use a software, okay, to provide the answer there, but when you have time, go ahead. And if you are taking notes along the way, write down the answer here as well. And it's only meant to be a quick judgment and decide. Okay, so now on our board, it's even power again, power of 4, even power. So we're in this column. I am already expected in my mind that both ends have to go in the same direction. Okay, and so further we're looking at the coefficient. It was a positive coefficient. It was that positive coefficient being a 7/4. All right, so that in that way, that's now just enough for me to have enough clue for me to decide right here. Positive coefficient and even power. So now left end and right end, they're both going up to positive infinity. All right, that's the y value. Okay, so now back to my program right here, my software program. Now I'm going to select right end. I'm going to select positive. Okay, left end right here, I am going to select positive infinity as well. Okay, and these should matches. Okay, with the actual answer key that's revealed by the software, and see if you are a student using the same software here that I'm using, and I'm not the only instructor using this software. To let you know, anyone learning from this lesson, then if you are a student, then you're gonna go ahead and hit submit, and as long as your answer provided here matches with the answer that's expected by the program, then it will mark you green. All right, so in that way, that's the answer right here, and now you can spend some time you can spend some time writing these answers into our note earlier. All right, so this time before I turn into the screen, I quickly wrote down the answer right there. So these are indicating what we want to look at in the left end, in the right end, in the left end. All right, and these are the actual answers that we're looking at. So that's how I note of what happened right there. All right, so let's now look at the next problem. All right, so here we are at a different problem right here. So how about let's describe the long run behavior, or the end behavior of this function f of x equals 13/4. This is a coefficient, and our power function is here x to the cube. All right, so let's write it down. And this is our part C of the example. All right, so very similar to the earlier problem. So part C here, I'm looking at f of x equals, and this is a 13/4 times x cubed. So we want to study what's happening to the function as x is getting to the right end. We want to look for that answer. We're going to look at what happened as x to the function as x getting to the left end. Okay, left end and right end. So now let's look for our answer right here. Okay, so our function is odd power, okay, and positive coefficient in front right here, positive coefficient. And so on the board here, we already had a clear deciding line right here. Odd power takes us into this column of decision. Okay, and now coefficient being positive coefficient. So now we know that the two ends have to behave in opposite direction. The two ends go in opposite directions. And however, now more specifically, since we are looking at positive coefficient, now right end points up, left end points down like that. All right, so in that picture, we have a clear answer. All right, so let's see what the software is saying. So now with the software, see, left end, in this case right here, left end points down. So I'm going to select this answer right here. I'm going to get that answer. All right, and then right end, x going to positive infinity. It's going to go. We're going to select that, okay, and the answer keys agree with that. And like I said, this is only for instructor only. I mean, if you are using an actual student version, you won't see this because that's the whole point of practicing. Okay, but you will instead hit the submit button if you are using the same software as I'm using here. All right. And so now in that way, now clearly, now the answer is written as following: y goes to, right, positive infinity. And then here y goes to negative infinity. All right, it's meant to be a quick one, but of course, being an instructor allow me to keep putting in some explanations. All right. And now let's call this one an FYT. For anyone who was already in gear with this kind of problem and have built enough experience, let's call this one an FYT right here. So out that same worded instruction of the problem. Okay, but now let's look at our function here being f of x equals minus 5x cubed. So for this one here, after writing it down and writing down the function, I'm just going to stick with the computer screen, okay, and show the final answer, and hopefully you will agree with mine. So it's minus 5x cubed. Now you have enough reasoning right here. Go ahead and pause the video to make your own the chart and then lead into your own decision. And then I will hop over to the computer screen and generate the final answer. Okay. All right, so now I hope you have had enough time looking at the chart to decide. So now right end will be going to negative infinity, and left end will be going to positive infinity. All right, and that's the answer that's expected.